This problem involves binary trees and working with the x-assigned change-x pattern. We're asked to write a new method for the int tree class called limit_path_sum that takes an integer specifying a maximum sum and that removes nodes so that the sum of the values on any path from the overall route to a node does not exceed the maximum. So we have a sample tree here, and we're told suppose that we're limiting to a sum of 50. We consider various paths through this tree. So if we were thinking about this node right here, for example, the path is from the overall route to this node to this node. And that's a good example of something that's a problem for us, because 30 plus 17 plus 37, that would be bigger than the maximum of 50. And so that's why that 37 isn't included. The 17 is included because 30 plus 17 is 47. That's less than the 50. And then going down to this node here, that is a sum of 40, so that would be fine. Over in this direction, 30 plus 15 is 45, so that's why the 15 is in there. But the right-hand subtree would make the sum be too big, and that's why it's gone after the call on this method. 30 plus 15 plus 4 would be 49, and that's okay. That's within our max, so that one is still retained even after this call on the method. We're told that when a node is removed, all of its descendants go away. So we're cutting out entire branches of a tree here when we see that that maximum is exceeded. I've set up a JGrasp file for us to work with, and I have a very particular tree that I've set up. I've modified this so that there's a constructor that makes a variation of this tree we were just looking at. So I'm going to use the debugging capabilities here of JGrasp and using this very specialized tree that I'm setting up. If you didn't have a structure viewer the way I have here in JGrasp, you could use a call on print sideways, for example, to see the structure of the tree. But I'm going to go ahead and set a little stop here. I'm making 2 copies of this tree so that when we're done we'll be able to compare the original tree with what we get after a call on the method. So here's that tree. It has the same data we were looking at before, but I've added a new level, some extra values down here, and we'll be able to take a look at the very end and see whether we've got the right structure. So it's just some extra testing in here to make sure that the method is working properly. But that's all going to be after we finish writing it, so let me end our debugging session and collapse this for now so that we can go into the int tree class over here. And I've set up a beginning here for our limit_path_sum method that we're supposed to write. Now, as usual, we're going to have a private version of this method. We could also call it limit_path_sum, and it's going to take an int tree node specifying the root of the tree, and the other parameters, well, it's probably going to take max. Any others? Well, we'll see. So the idea would be that we're going to make some kind of a call here. The public method will make a call passing in the overall route and the max that it was given. So it would pass in those values into the private method, and the private method would do whatever it's going to do. So that's a good start. We'll see that this is actually going to turn out somewhat different by the time that we're done. We want to think about different cases, as usual, with the binary tree. So a binary tree can either be empty, or it can be a root node with some data and a left and a right subtree. So if the root is null, that would be an empty tree. In the case of the empty tree, there are no nodes at all. So the whole point of limit_path_sum is that it's deleting parts of this tree. And if there's nothing in the tree at all, then there wouldn't be anything to do. So this is a case where we would say if root is not equal to null. If it's not an empty tree, then that means that it has a root.data and a left and a right, and we should figure out what to do with those. So that means we have some node in the tree, and we want to be thinking about whether this is a node in the tree that we want to get rid of. So we want to be thinking about the max, and we want to be thinking about the path sum. So if we've gotten to some node in the tree, if we've gotten to here, for example, we want to figure out that the path sum is too big. If we've gotten to here, we want to see that the path sum is still okay. So that's going to require a little extra work, something that we hadn't included here before. There's several ways to approach this. We could have max change, for example, that we could pass different values of max as we see, for example, that we've eaten up 30 of our max. We could pass a different max to the next method. But I think conceptually it's a little easier here to imagine that what I'm going to pass is a sum that tells you what's the sum of the path up to but not including this node. So if we were making a call on this node here with the 4 in it, we'd pass it this 45, the 30 plus 15, the sum so far. What does the path add up to before we entered this node? And so that's the value that I'm intending that we pass here as an extra parameter. Often figuring out these extra parameters is really the key to solving a tricky problem like this. Now we have to give an initial value, and initially we haven't looked at any nodes, so 0 would be our sum initially because we haven't given it anything. So what we can do here is we can update the sum. We can say, let's take the old sum, the sum that we had so far, and let's add into it root.data. So that will update this sum so that we've included the sum for this particular node. And then we want to figure out, is that a bad sum or not? I mean, we're supposed to make sure that we don't exceed this maximum. So we can see if the sum that we would get, including this node, is greater than the maximum that we're supposed to be looking at, well, then that's a bad node. That's a node that we don't want to have in this tree. So we'd want to remove the node. That would be kind of something to do. That's what we want to do in that case. And otherwise, that would be a node that can stay. And what we want to do is we want to deal with its subtrees. We want to kind of deal with getting rid of any nodes that might be in the left and the right subtree. So this is kind of the test, as we add in the root.data, see whether we've exceeded our sum. If so, get rid of it. What I'm going to do to fill in this idea of removing the node is I'm going to say, how do you get rid of a node? Well, let's set the root to be null. That we'll just kind of chop off this part of the tree. Instead of having the root point to the node that had this data in it, we'll get rid of it. And we were told in our problem statement that we should get rid of all of its subtrees as well. So when a node goes away, everything goes away. The entire subtree goes away. And then otherwise, what would we want to do? Well, we would want to limit the path sum in root.left using the max and the new value of sum. And we would want to limit the path sum in root.right, passing it the max and our new sum. So that would be the way to prune the left and the right subtree, potentially, if they had values that would exceed that maximum. You can go ahead and close this if that was for the test on root being null. The logic here is pretty good. In fact, we've almost finished this problem. We've almost solved it. The problem is that when we tried setting a root value like this to null in the middle of a method, that root was passed to us as a parameter. And it turns out that we can make a local change to that parameter, but that doesn't have any effect on whatever was passed into this as a parameter. If we want to be able to actually change what was passed into this, then that's where we have to use what was mentioned on our slide here, the x-assign change x pattern. So what we want to do is to change this method so that it's going to return an int tree node. It's going to return the value of root when it's done. So we're going to return the value that root has after the method finishes executing. And then every call on limit path sum has to be turned into that form, x assign change of x. So there are 3 calls on limit path sum, and we have to fix each of those 3 calls. In this call, the x that we're passing is overall root. So we just follow that pattern and set this to overall root is assigned to what comes back from the call on limit path sum. Here, it's root.left that's being passed, so we set root.left to be what comes back from this call. Here it's root.right that's being passed as the parameter, so we set root.right to whatever comes back from this call. And again, by having the method return the value of root at the very end, and by doing this assignment where we're passing in an overall root and then potentially reassigning. We're passing in a root.left and then potentially reassigning. we're passing in a root.right and then potentially reassigning. This is what allows us to change root in the middle of this method and to have that change actually change the value that was passed as a parameter. So this is the way, this pattern, to get this to actually change the tree as we want it to. Let's go ahead and compile and make sure that we haven't introduced an error here. Let's go back over to our method here, and let's go ahead and open back up our debugging window here, and let's go ahead and debug it and see what we get. So when we tell it to debug, we have our original tree here. Let's go ahead and set up our tree T, and then we're making a call on the limit path sum. So let's go execute one more line of code, and we'll take a look and see what that T looks like. And the T has lost lots of things. This looks somewhat similar to the tree that we had before, the 30, 17, 15, minus 7 and 4, 30, 17, 15, minus 7, 4. So that matches what we had in our original. But there's also kind of this next level of the tree, and of that next level, the 10 and the 1 were retained. Let's scoot this over here so we can take a look at the original tree and see whether that was the right answer. And so remember that when we were going down this path here, 30 plus 17 is 47, minus 7 is 40. So the 10 got us a sum of 50, so that was okay, but 11 would take us to 51, which is too much. So it's actually right that it included the 10 but not the 11. When it chopped off the 37, it also chopped off whatever came underneath it. When it got over here to 30 plus 15 plus 4 is 49, then it could add a 1 to be 50, so that's why that node is retained. But adding a 2 would take us to 51, so that didn't work out. And then, of course, we chopped off the entire branch over here. So it's working. The code is working. It's we're looking at our test cases here. We can see that that's actually working out. Let me end our little debugging session here, and we can take a look back again at the solution that we had come up with to this problem.